Hello and good morning, everyone. My apologies, my voice is not 100% today. And my name is Kanchana Tilakaratne, and on behalf of the BEST team, and that it also includes Shasha Rubin and Barbara Steven, I would like to welcome you all to our BEST seminar today. If you're first if you join BEST seminars for the first time, allow me to share a few words about the Besser Seminar Series. So it is actually named after Sir Adolph Besser in recognition of his donations that helped build the university's first computer here at the University of Sydney, which was operational by 1956. That was sometimes simply called the brain. And at that time, graduates from our school also called Besser graduates as well. Okay, so let me get back to today's talk. And actually, COVID has showed us the way to take our seminars around the world. And we heard from, many distinguished speakers from different parts of the world over the last few months. So today we have a distinguished speaker from University of Houston, Professor Xu Hang. So let me introduce Professor Xu Hang very briefly. Xu Hang received a bachelor's degree in electrical engineering from Tsinghua University, and then PhD from electrical engineering from University of Maryland. He is currently John and Rebecca Moore's professor in electrical and computer engineering, as well as computer science at the University of Houston. His research interest covers a broad range of things from security to wireless networks, game theory, and multimedia. And he has also received many awards in the past, including an SF Career Award and many Best Paper Awards. And he's also currently a CM Distinguished Speaker. And so without any further ado, let me open the floor for Dr. Xu. And today's talk will be 50 minutes, about 50 minutes, and then we have about 10 to 20 minutes of questions after that. So please join us a lively discussion at the end of the talk. And with that, Xu, floor is yours.
Okay, thank you very much for introduction, and thank you very much for invitation. And it's my great pleasure to share my former PhD student, Dr. Jin Li's work on the crystal economy, the economic mechanism behind the blockchain. And this work is done by Dr. Li and my current PhD student, Daniel Dou, and supported by NSF. Dr. Li just found a new, very good job in Wall Street, twice of my salary. Yeah, and so he has no time to join with us, but Daniel is with us just in case I cannot answer your question, and I hope Daniel can help me for that. Okay, and here is the outline. First, we have the introduction about the basic about blockchain, and then we talk about the crypto economy, and specifically we talk about contract theory. Then based on this, crypto economy, we give two examples. And finally, we have some other work and the conclusion. So this is the history of blockchain. It's starting from 1980s about a Merkle tree, and then go to this crypto-based payment and the Byzantine general problem, idea of chain, and then begin to have the proof of work concept. And then finally, we have this decentralized digital current concept. And in 2008, Satoshi, invented Bitcoin. And nobody knows whether or not this is a guy or a kind of a nickname or kind of organization. But the Bitcoin seem to be the very successful one. And I will tell you why later. So what is the blockchain? The blockchain is a distributed, decentralized digital ledger that exists across a peer-to-peer network. So here, typically, we can have the different type. For example, if we have this centralized one, so we will have the centralized control, and then everybody kind of connected to it. It looks like a bank, okay, the central bank, and everybody just connect to the central bank. And then we can have the distributed, for example, the SWIFT system for different countries, United States, Australia, China, and something they have their bank, and in the middle they can kind of using the SWIFT system to switch to exchange. Oh, by the way, I should cross this line because this part may be Russia. I'm just joking. Okay, and for this kind of decentralized system, everybody is a P2P case, so there's no central node at all. Everybody is just equal to each other. So in this case, okay, we have the block. I mean, block for the different everybody on the block, and then we have the block header, and which have this kind of a hash of n-1 header linked to the previous one, and then we write down all the transactions. So by doing this one, everybody have this kind of ledger of all the other. So in this case, okay, nobody can lie. So basically, the blockchain is a decentralized situation. And the question is that, okay, for consensus mechanism, here we need to have consensus mechanism that everybody agree with. The question is that who will be the one has the right to insert the next block into the blockchain? So basically, okay, you can think about it. Hold on a second. Give me 1 second. Okay. Give me 1 second. Okay. And with the consensus mechanism, the information announced orderly to all users without involvement of the third party. So in other words, okay, the blockchain is growing, and the new block will write down this kind of the ledger of all the previous transaction. But how could we do the consensus such as select whom to be the next one? And then without the involvement of the third party, there's no centralized control to give me the instruction. So there are typically two types. The first type is a proof-based consensus, and basically have the excellent scalability, low transaction throughput, and high delay, and such as Bitcoin and Ethereum. And then there are voting-based method. So basically, okay, they are voting instead of proof of work or proof of stake. And in this case, they have this kind of very excellent delay, but not quite stability. And then example solution is a Byzantine fault torrent or practical Byzantine fault torrent, etc. So basically, okay, for proof type, we have the proof of work. So basically, the core of proof of work is the competition of the computer power. The nodes are called miner. So basically, all these machines try to all over the world, using most of the energy of the world, use its computer resources to hash operation to compete for the right to generate the next block with bonus. So the winner will be the first one who obtain a hash value lower than the announced target. So this is the proof of work, right? And this is how why this kind of mining machine, okay, everywhere. And then, oh, sorry. And however, okay, many countries like China or even the New York State already kind of, forbidden this kind of mining operation because it's really wastes a lot of energy for that. And then, okay, recently, okay, they want to upgrade the proof of work to proof of stake. So the concept of the proof of the stake is that the coinage use the proof of stake block to avoid the high computation complexity of hash operation. The coin age of an unspent transaction output is equal to its value multiplied by the time period after it's created. In this proof of stake, a higher coin age will lead to a higher probability for the node to win the right to create a new block. So the proof of work, so basically everybody working, proof of stake, if you have old money or your money is sufficient enough, and then, okay, you have more rights to do that. So basically, okay, this is depending on how hard you work, this depending on how old and how rich you are, okay. And then this is the first type, and the second type is this kind of voting based. And the voting based, basically, okay, everybody vote, but there's a kind of a Byzantine problem, Byzantine attack problem. The so-called Byzantine attack is that we have n general, and how many traitors the system can be tolerated, such as, okay, the whole system collapse. And the fault tolerance is 1 over 3 by certain proof. And then the the other type of blockchain based on the voting based, like this BFT and PBFT, is based on this kind of voting based. And here is a kind of comparison. With this POW or POS, you can link a lot of nodes together. However, because everybody have to track all the others kind of node, so the transaction speed is very, very low, typically less than 100 per second. On the other hand, okay, for this kind of voting based, they can have this kind of very quick kind of transaction. So basically, okay, sufficiently enough for this many credit card. However, the number of nodes can be small because consensus space, this type of thing is take a long time for them to converge. So basically, okay, this is a trade-off between these two, and the goal is to push this one into this boundary so that we can not only have this kind of large number of nodes, but have a large number of low latency, and the number of transactions per second will be also high. So this is the goal for this. And typically for blockchain, you have this two camp. For the first camp, it belongs to the computer science part. So basically from the implementation point of view, so they talk about cryptography, chain of block, and consensus. Sorry, okay, consensus. So basically, however, this lack on the they have a lack of this incentive mechanism. The second part is from this crypto economy point of view. So basically, this part, okay, they will provide the incentive to the rational user to do that. So the first part, the first camp is typically from computer science point of view to against the malicious user. Well, the second part, crypto economy, is typically from this economic people to give this incentive to the rational user so that, okay, the system can be better. And so let's come see the first camp of the study, which is this Bitcoin. So the first miner that solved the mathematical puzzle will obtain the privilege to create the next bit. So we have mentioned this before. The Bitcoin use a block reward and the transaction fee to compensate the miner for their work and to avoid and to incentive miner to the longest chain. And use the Bitcoin network anonymous and entry exit at any time, and any two of them can communicate with each other relatively quickly. And here they have the different model, honest model, unconditional, uncoordinated majority, coordinated majority, bribing attack, and so on. So the Bitcoin using this crypto economy to solve the problem. First about the weighted assignment problem and how to receive the SIBO attack. So they are fake ID, just like Twitter. Okay, I'm just joking. Okay, and then we have this incentive problem: how to motivate the unknown participant to behave correctly. So you can see that, okay, even in the first camp, the reason why Bitcoin is so successful is it's already using some concept about the crypto economy to give the incentive for the rational user. So what is the relation between blockchain and this crypto economy? The blockchain project and the blockchain-based solution are the instant crypto economy, and like a Bitcoin, Ethereum, and the proof of work, proof of state, and so on. So what is the crypto economy? So with VLAT, okay, at 2015, the crypto economy is an application of incentive mechanism to the information security problem, and this is a god of this in the crypto economy. And so this is the security from the cryptography. From this first camp, they try to solve the malicious attacker problem. Well, for the incentive, it's basically about the rational participation. And those people are not the purpose of the malicious attacker is not for their profit, but to attack the system. Well, for the rational participation, their rationality is to make money. So you can see that, okay, if you have this kind of assumption that, okay, the user is in the rational participation, then we can use the crypto economy. Well, I mean, if you're thinking about the malicious attack, then you better go to the first camp. Okay, so this is the relationship. So my PhD student is working on the second part, and second camp. So this the key question: how does the incentive secure the distributed system? So we can have the reward, increase the action token balance if they do something good. like the block reward and transaction fee and so on. We can have this penalty, reduce the actor's token balance if illegal behavior occur. For example, we can have the security deposit. When you go to the hotel, okay, they will give you, they will get $200 first. So just in case you break something, right? And then we have the privilege incentive participants by giving them decision-making right. So like in the voting weight, okay. So basically, okay, this is the case. Okay, how should we determine the incentive mechanism? So this is basically fall into the category of mechanism design. So how could we design this kind of incentive? So we have different type. One typical type is called auction theory. The one very simple, very kind of obvious. This famous one is the VCG algorithm, but this is not what I want to concentrate on this talk. So I just found a kind of a video so that it can explain the auction theory. And auction theory is also the Nobel Prize winning, and so it's very complicated. But this video explains it well.
Anyone else? Going, go! 210!
Sorry, it's a black joke. Okay. Anyway, and then the other type I see in the literature is the coalition game. So basically, okay, using the merge and split method to find this kind of partner that they can work together. And if they find somebody that can bring the mutual benefit, they will marry together. And if they find this, they cannot work anymore, then they will divorce each other. So basically, this is a coalition game. And in this talk, we concentrate on the contract theory. So what is the contract theory? The contract theory studies this economy actor can do to construct a constructive agreement, generally in the presence of information asymmetric. So basically, the key point for contract theory is the information symmetric. So basically, okay, for example, this kind of the left people know this kind the right people know the left people what they need, but the left bank do not know the right one what they are. So in this case, okay, it's called information asymmetric, and also this information is very private. So if you have the hidden information, in this case, we call it adversary selection. So basically, okay, this agent belongs to different type, but this kind of, employee have no idea about what type of these people are. So how could we design a product? How could we design a contract such that those people, even though I don't know their type, they will select the right type of contract that reveal their truthful identity. So this is called adversary selection. And then, okay, the other thing is about the other is hidden information. The sender sends the private information may convey to the receiver through the observation action. So the second type is about signaling. So by interaction, for example, okay, at first I don't know Dr. Trump for very well, but after so many interaction with him, I know him quite well. So this is so his private information. Is I know most of them already by interaction. So this is called signaling. I'm just joking. Okay. And the third type is this kind of moral hazard. So it's a hidden action. So basically, okay, I cannot monitor my student working. So whether or not they are not working or not, I have no idea. So this one, their action is hidden to me. So how could we design the contract such that okay, they will work hard, and so this is a moral hazard, and this contract theory have won multiple Nobel Prize, such as this 2014. Well, let's give some example about my adversary selection and moral hazard of my PhD student. So before I try to hire my student, I want to ask, okay, I mean, what type of the student is, what you want to do, and then the student will always say, okay, I want to become a professor, I want to do the research, okay, and because what they really want to do, looking for intern, or the secret plan become a baker, rock star, or something like that, I have no idea. So in this case, what I can do, so I will design the multiple contract. For example, I really have no idea about whether or not my student is good at mathematics or good at programming. So if I ask them, okay, and I mean, are you good at math or are you good at programming? And my student always say that, okay, I'm good at both, right? As a matter of fact, it's not the case, okay? So their information is hidden to me. So in this case, what I can do, I will design two contracts. One contract is if your mathematics good, you dig into the mathematical part, and then I will find the application for you. So you only study the mathematics core and then apply to the new the application I provided. And on the other hand, okay, if your programming is good, then you go to the most cutting edge scenario to set up this scenario. And in my hand, I have already accumulated many different tools for mathematics. Then I will teach you this mathematics and you utilize one of them to the new scenario. So I provide two contracts. And then the student himself or herself know that what he or she good at. And then they will select the project, select the contract that fit him or her best. So in this case, okay, by designing two contracts, I let them truthfully reveal their own identity. So this is adversary selection. So after hiring them, okay, how could I make sure that they are working? So this is what the PhD thinks, parents think they are doing, what I think they are doing, when I'm in the lab, okay, what they are doing, and when I'm on the vacation, what they are doing. Okay, so this is a problem. Okay, I cannot monitor them all the time. How could I make them kind of work that, okay, I mean, work with the same goal as me? So in this case, I designed the contract like this one. So typically for this university student, they will graduate with a fixed amount of years, 4 years or 5 years. But then there's this problem. The problem is that the first 3 years, they will party. In the last year, they will go to the PhD advisor's office every day and crying or something like that. And finally, the PhD student advisor become the student. Yeah, but that is not right contract. My contract is that, okay, I have, if you submit the paper and how many score, and if you accepted a journal, okay, how many score, and then at least one journal have to be accepted, and then you accumulate it to a certain score, and then you can graduate. The fastest PhD is 2.5 years. The slowest is 9 years. Okay, the 9 years because he has a family problem. Sometimes he has to work for his family. But then in this case, okay, align my student interest with my interest, because my interest is to publication, right? New research. And my student interest is to graduate as quickly as possible so that they can earn big money. So by designing the correct contract, I align the employee and the employer's kind of interest together so that I don't need to monitor them. They will work very hard. Okay, so this is a kind of moral hazard after employee. How could we design the contract? Okay, so let's come back to this crypto economy. So there exists information asymmetric. The participation are anonymous in the blockchain. Most of the population are rational and not willing to reveal their private information, like how capable they are and how many kind of computation power they have. They always say, I can do everything, right? And the number of participation also is very large. So the contract theory can overcome the information asymmetric with a large number of rational users. So here, in the first one, we try to use the contract theory, one of them, to design the incentive for this one. So, and sorry, okay, we can have this different type of contract theory by providing incentive like the reward and the penalty and the privilege for the decentralized blockchain so that, okay, they can behave better. So this is basically, okay, the blockchain history, what is the different what is the specific crypto economy, and blockchain have two camps. Okay, we concentrate on the crypto economy part, and for crypto economy, they have different type of game, and we concentrate on the contract theory. And then next we give two examples for this how to use the contract theory for the blockchain. Okay, so the first one is this contract-based approach for security deposit in blockchain network with shard. So basically the blockchain with shard is that the blockchain is large. So typically they can divide into the different shard, and each shard have like the sub chain. So they compute parallelly, and occasionally they merge to the beacon chain. So in this case, okay, they can increase the throughput. So the shard is used to realize the scalability, and the participation entry into the parallel subgroup, which is responsible to generate subblock. Okay, this is already explained. So in order to, for the proof of stake, okay, in order to join this kind of, a blockchain, you should have some kind of security deposit. And just like I mentioned, if you go to a hotel, they will charge you $200 first, just in case you break something, okay? And the deposit, generate greatly exceeds gain, can provide sufficient security incentive. So just if you don't, basically, otherwise you lose you have to behave yourself, otherwise you lose this deposit. And currently, okay, for this current standard, for this, this Ethereum, they use this 32 coin as a kind of security deposit. So it's a fixed one, 32. So with the 32, okay, you will have the incentive. Otherwise, you cannot enter. I just checked 32. Okay, is about 80K US dollar now. Okay. So I think maybe for you guys, okay, Australia rich people, okay, it's very cheap. But for me, okay, I don't think, okay, 80,000 US dollar is a small money. So basically, I cannot enter it. So this is a kind of motivation. So the motivation is that, okay, how could we motivate not only the rich people to join the Bitcoin, to join the blockchain, but also the relatively kind of, not that rich people also can join. Okay, anyway. Here is the system view. We let the beacon chain with a weak leadership be responsible for design the contract. So we submit the deposit and receive the deposit receipt. And the validator are randomly selected into the different committee, and proposer propose a new block and a tester to confirm the block. And the block from one time slot will merge into the beacon chain, and the block in the beacon chain are finalized, and validator obtain the reward. So basically, okay, this is a protocol that you can use to really implement in the POS blockchain with shard. Okay, so this is basically, okay, they are kind of protocol. Here we just use a plain English to explain to you. Okay. And for contract model, so here is what we propose. Okay, so beacon chain design the contract according to the user's type information. For example, the user type, whether or not you're rich or not, I don't know. Okay, so I design a multiple kind of type of contract for you to select. And the different validator selects the corresponding contract, and the validator submits the deposit to beacon chain, and the beacon chain issue the rewards or charge a penalty on the validator. The beacon chain has asymmetric information about how much validator can pay. So this is the thing. Okay, I really don't know whether or not this player how rich it is, but I will select a different kind of contract with a different security deposit, so that, okay, different people will kind of select as a select. And for example, if I go to this I say, okay, Top Grand Hilton, okay, they probably charge me for $500 deposit. If I go to some kind of, Day Inn or something, Holiday Inn, something like this kind of relatively cheaper one, they probably only charge me $200. So, but the key question is that, okay, how could we design this kind of, security deposit in contract theory point of view, so that okay, you have nice property to against the information asymmetric. So here we have the system model. We have validator utility model. We have the different type. Okay, here we have type theta1 to n different type, depending how rich you are. And then the utility function is this is your type. This is evaluate the reward that obtained from the beacon chain. So this is basically okay. This is if I select this type, and then this is a word that I have minus the computation cost I need to do, like the mining, and evaluate the penalty for the type I validator. Okay, so basically this is the utility function. And then for the constraint, we have two constraints. Okay, the first one is individual rationality. So for this validator, if my utility is negative, I will not join. I join and I will earn the money. Otherwise, I will leave. Okay, this is the first one. And the second one is the incentive compatible. So basically, okay, the contract designer will design the multiple contract such that okay, if the user is own right, is own type. For example, I'm the ice type. I select the ice type kind of contract. Then my utility function will be larger than if I select the J's contract. J is not equal to I. So in other words, okay, I design the multiple contract such that okay, for those validator which have the private information that don't want to reveal to the contract designer, this contract this kind of player only selects their own type, their utility function will be maximized. If they pretend to be other type, their kind of utility function will worse than the truthful reveal type. So in this case, we provide this incentive compatible constraint. In this case, okay, we can ensure the user will reveal its truthful information. It's just like I give the student two contracts. One contract is theory-based, the other contract is coding-based. And then, okay, if the theory guy selects a coding type of contract, he will face a much difficult by programming. On the other hand, the programmer guy selects the theory guy. He has to study a lot of theory and he will get headache. So if he is rational, he will select the one that fits him or her best. So this is this constraint means, okay? And then we have this profit obtained by the validator. So basically we have this ugly type for the utility function. This is the evaluation function regarding the validator type, time, type, and reward, minus the total cost for the reward. So basically, okay, if you do the good work, I will reward to you. The reason for such kind of ugly type is because later you will have the closed form solution. And also this one can have any physical meaning for that. Okay, this comes from the literature and it works. Okay. And then the problem formulation is that, okay, we try to select the different contract, and then, okay, select the different contract, and then, okay, the evaluative function, and then such that, okay, the different user will select, and finally, okay, their performance will be maximized. So basically, this is the problem formulation for this. So for such kind of problem, for if it's a small network, it's okay. But typically for blockchain, they will have thousands of users. So this become a kind of a very complicated, many different constraint optimization problem. And then here we need to have this constraint reduction, and depending on the monotonicity and individual rationality constraint reduction and the individual incentive compatible constraint reduction. And then in this case, we can remove any kind of constraint, such as such kind of optimization can be calculated real time for the large system. Okay, so this is thing, and we have this kind of optimization, and here is the result. And here we try to have the direct expression, and here we can, the reason we have this ugly form because under constraint, we can have a very nice closed form expression for this. Okay, and here we show you the result. So for the first figure, here we have the different type. For example, this is a type 3, this is from 0, 1, 2, I think, okay. This is from 0 to 9, okay. Here there's a, I think it's right, okay, sorry, it's right. So here is a type 4 user, and then this means, okay, the type 4 user select the type 4, it will have the highest performance. This means the type 6 user select type 6, it will have highest performance. If they pretend to be richer or poor, and then their payoff will be smaller. Okay, so this kind of simulation result demonstrates that, okay, the proposed approach can ensure the truthful review of the user, I mean, for their private information, as long as they are kind of rational users. On the other hand, okay, on the right figure, we show this kind of different type. This is a calculated result about the deposit. And this 32 is the current standard. So basically, okay, everybody pays 32, and then it gives the, I mean, it's only the richer people's gain. However, for example, for those people, for the type 1 and type 5, it's a relatively poor people, they will not play. Okay, and so on the other hand, okay, for this, for our proposed one, this is a kind of security deposit that we calculate. The optimal security deposit that we calculate. So for those kind of poor people, they will have the less kind of one, and for the richer people, they will have the higher deposit. However, this is a payoff for each round. For richer people, they will get more payoff. For poorer people, they will have less payoff. And let me give you an example. For example, if I went to Las Vegas, okay, and then okay, the only thing I can for a US professor, the only thing I can afford is this 25-cent this slot machine, and then this 25 cents is very low, but the payoff is also very low, right? And take me a long time to get a little bit of money. However, I remember there's a conference in Monte Carlo. Monte Carlo is a country between the France and Italy for gambling country. This is the richest country in the world. Okay, and then they have the Royal Casino Royal. This is 007. This casino, and then I try to enter it. They asked me the security deposit of 10,000 euros. And I don't think I can afford it. So, but on the other hand, okay, they can earn a lot of money for this. So this is you can see that, okay, by using the contract theory, we design the different deposit and the different payoff for different people. Okay. And so the summary of the first work, we use the contract theory to determine the flexible security deposit. The flexible security deposit can guarantee the economy incentive without reducing the security incentive. So everybody can play, okay? And so here in the next talk, we try to using the adverse selection, the moral hazard, and the cycle of gain and reward to overcome this kind of to provide this cyber insurance design for this sharded blockchain. Okay, so this is the second work that we want to have. So we have the cyber security design. So the background is okay. Here in this case, we have for the proof of stake. There's a significant attack called discouragement attack. So basically, the discouragement attack means the attacker would act maliciously inside the consensus mechanism to gradually reduce the other validator's revenue. So basically, okay, everybody just work together, and then okay. And so how could we explain this one? So basically, okay, at the beginning, okay, in a company, everybody worked together. And after that, okay, after the project got shipped, and then they get bonus, right? And then, okay, suppose everybody kind of work equally hard, okay, they will divide it. However, for this discourage management, they will only reward those people that is their buddy, and for those people that okay, not their buddy, they will kind of reward zero. So over the time, those people will feel unfair and leave the company. So gradually, okay, those attackers will increase the number of the number of this attacker will increase until they can launch the Byzantine attack. So basically, this is called discouragement attack. Okay, and you will face that kind of things quite often if you go to the company. Okay, right before the project get finished, the manager will send several people to the project to dilute your contribution. Okay, so this is a very typical trick. Okay, anyway, and so the discourage attack means that the attacker would act maliciously inside the consensus mechanism, gradually reduce the other thing. So this is what I mentioned. So basically, give this only their own body the credit, while the other get discouraged. So this is our reward. I think this is basically a similar story. The key point is here is that the fewer validators signing the message, the lower everybody's reward. Okay. Anyway, so in order to overcome such kind of problem, and for this Vitalik explore a new type of attack that can bring down the whole blockchain. And so they propose this kind of, to prevent this attack, this Vitalik presents this, the system should set a withdraw delay instead of allowing the validator to enter access quickly. So in other words, okay, if this body kind of try to quit, and then they will try to kind of think whether or not, okay, why this one want to quit? Maybe there are such kind of a discourage attack to do an investigation to see whether or not, okay, this guy really gets the discouragement. Okay, so this is what they propose in the literature. So the blockchain network require appropriate incentive to encourage the validator to stay online or neutralize the whole system risk. So basically, we have this discourage attack, and in order to overcome this one, we have the cyber insurance framework. So basically, we have the insurance to make sure that, okay, those people, if they get attacked, they will get insured. And also, okay, we use this we change the withdraw delay into the contract staggered game. So here, basically, okay, we use the contract theory framework to replace the existing withdraw delay for this discourage attack. So here's the system overview. The main change is recruiting the validator, and the malicious validator are blending in with the other honest validator. Let the beacon chain be a temporary leader to design the contract. The block manager sign the insurance contract with the cyber insurance. The cyber insurer will pay the claim for the victim if there exists a discourage attack. And then, okay, we reward the distributed fusion and expected cost. So basically, this is a cost for this this is a censored validation cost, validator's loss function. This is uncensored one. And here, this is basically, okay, this is probability of sensing. So basically, okay, they don't have this kind of all the time to check everybody. So this is the probability to check censor whether or not those people are kind of working well or not. So for example, in US, okay, every 6 years, there's an ABAT. So basically, undergraduate teaching is evaluated by ABAT. So basically, make sure that, okay, they are kind of teaching according to a certain standard. So the different university for transfer students, their credit can be transferred equally. So in this case, okay, for ABAT, this ratio is 1/6. Okay, and the cyber insurance utility is that, okay, they have this premium and claim. So the premium is basically, okay, they collect the money, and the premium is that if there's a kind of attacker got this kind of attack, then they will compensate for that kind of attack. And then the blockchain infrastructure provides provider act like the intermediate between the cyber insurance and the validator. So this is a blockchain gain from the validator. This is a compensation paid for the cyber, and this is compensation for the validator, and so on. So the validator utility function for a certain range of actives, we model the truncated normal distribution, which is this one. So basically, the distribution of this one we can quantify. And then, okay, if the validator does not send any contract, it will bear the total kind of loss by the discourage type. So this is quantify. If we don't buy the insurance, okay, if you have a car accident or you have this discourage attack, what you need to pay. And with a single contract, for example, Obamacare, only one, okay, so this is what you pay. And you have a miscontract, so suppose you have this kind of multiple competitors to compete with each other, and then this is what you need to pay for this. And this is the overall utility function for this kind of each player. This is the basic cost. And then we have the problem formulation. We have the utility function of the cyber insurance for the stage one is defined in this one. And then for the second part, the second layer, the first layer is the insurance. The second layer is the blockchain infrastructure provider, which is the middle layer. They have the utility function of this one. They try to optimize their performance under the constraint that, okay, this validator or this player will satisfy this kind of individual rationality or incentive compatible and also truthful review type constraint for this one. So this is basically combined with this kind of stagger game with the contract theory to formulate this insurance that provided that's providing the insurance to the blockchain infrastructure, such that just in case the validator got some kind of discourage attack, they can get compensated, and they are willing to pay for the insurance. So basically, the optimal solution is this contract framework. We can calculate for the constraints, this part. We can calculate the closed form solution, which is in this one, put into the constraint. And the second stage, we can get a closed form solution. And in this case, we put into this kind of first stage for the cyber insurance. Those one will put into the closed form constraint in the cyber insurance. And finally, we get a cyber insurance based optimal strategy. So this is called back induction from the second stage to the first stage. Okay. And here we show several results. So the figure 2 presents that the premium in the both case increase with the validator type. So basically, okay, if you are kind of richer, then you want to have the better service, and then your premium is high. And then this is a single contract, and also this is a mixed contract. And so basically, okay, if you only have one insurance company, and you don't have the private company, you only have the Obamacare, and then this is your loss function. However, if you introduce a private company competition, and then this kind of, the loss will be lower. And the last figure is basically the similar case. If you belong to a certain type, then you select a certain type of insurance, and then you will get the best performance. So in other words, okay, for example, for PhD students, they will typically select a kind of very cheap insurance, right? And I think for this kind of big Hollywood star, okay, J-Lo even have even have insurance for certain part. Sorry, okay, I shouldn't say that part. Okay, certain part of her body for the insurance. And so basically, okay, you can see it's kind of different. Okay, so basically this is revealed information. Okay, okay, so this is for detail. We show that okay, for contract theory base, we work for this two kind of type. Okay, we have 5 minutes. Okay, we have other type. So basically, first one is the voting weight with the signal model. But basically, you can using the signaling to gradually understand, okay, who has the more power. Then in this case, we can have the higher voting. And then we have the random contract. So basically, okay, for different type, somebody want to take the high risk, somebody want to take the low risk, then we have the random contract so that the different type of people can play with the game. And then we have this kind of crypto assessed stability. So basically this for stability, stable coin. And a few days ago, we have the stable coin Luna, right? Which becomes 0, okay? And here is basically, okay, using this kind of option, just look like an option in the stock, okay? They try to kind of, can do the stabilization for the coin, okay? And the conclusion is that, okay, we started 2 categories of economy incentive, crypto economy and by using the contract, by using the penalty and penalty, which and as well as this reward. And then, okay, so basically, okay, there are different types. So because for contract theory, there are 6 different types. Here we only show the 3 of them. And then for incentive, beyond these 3, we also have different, and also for blockchain, we have the different type. So by all these combinations, we can see many kind of research work can be done. Okay, and oh, sorry, wrong way. And finally, okay, and I hope that the COVID will end soon. And then, okay, after that, okay, you can visit our website, web, and in our group, okay, we have many kind of visitors. Except for study, we do everything else. So welcome to Houston. And also you can go to this website. This slide will be there, and also many video, many PPT, and many kind of code. And you can feel free to use them. And I hope that the cooperation can be on the horizon. Okay, thank you very much.
Thank you very much, Shu, for a very detailed presentation. And it's time for questions. If you have any questions, please feel free to unmute or and talk, or you can put your virtual hand up if you prefer to do that as well. Okay, let's give some time for them to gather their thoughts while others are, gathering their thoughts. Shu, may I ask a very high level question? You presented these 2 strategies and, contract based strategy mainly we presented it in general, saying blockchain, but what kind of a real application that you think this kind of approach is more suitable for? Is it, let's say, a new cryptocurrency, or is it a different blockchain application?
Yeah, I will say that, okay, for the blockchain itself, if you really kind of care about the blockchain, using as a future currency, then okay, by using such kind of things, you can make it maybe my limited knowledge, okay, you can try to make this kind of coin make more sense. However, currently for this kind of cryptocurrency, the purpose is to make your money to be my money. So you understand my point, right? They are not designed the coin that make it usable for the future. They are designed the coin such as is a kind of so basically, okay, they just like Luna, okay, and the South Korea guy, okay, get all the money, right? 60 billion, right? And so basically, okay, that is the problem. However, the blockchain itself indeed working in many applications. I know that, okay, now in China, if you go to see some kind of sushi store, they have this QR code. You scan it, and then they will tell you, okay, from the beginning where this fish got caught, and who processed, how long it takes, and where before it's in front of you. So this is already implemented by the blockchain, so that okay, guarantee that okay is freshness. And this is just one example. Okay, and but I believe that okay, Web 3.0 will be there, and currently we have Web 2.0. What we kind of create online belongs to the other. In the future, for Web 3.0, you will have this kind of NFT, non-foldable token. So whatever you created, it's not only working in Amazon, but also working in Alibaba. Not only working for the YouTube, also work for the TikTok. Okay, so in this case, you have the digital property. So in this case, okay, blockchain must be there. Okay, so for Web 3.0, this kind of blockchain technique will be behind it. And such kind of blockchain will give an incentive for this gigantic amount of business in the Web 3.0. So that will work, okay. And also for Metaverse, somewhat okay. I think Metaverse is it's a plausible, but might not like a Web 3.0, which will be there. But for Metaverse, okay, this blockchain must be there, right? When you appear on this Metaverse, no matter which company you go to Facebook or you go to Amazon, okay, it is you. They will recognize it's you, uniquely you, not some kind of fake ID, right? So the blockchain must be also be there. So this is my answer to you. I will not touch this kind of coin because when they design it, we are not using the mathematics to design the system that is usable for everybody. They are using the mathematics to make your money to be my money. So, but on the other hand, for the Web 3.0 or Metaverse and some other application like the sushi, okay, this is indeed for the benefit of the common people like us. Okay. Anyway, I hope I answer your question.
Yeah, thanks, Shu. So let's see whether we have any other questions.
Hi, Professor Chu.
Yeah.
Oh, sorry.
Yeah, I have a question.
Sure.
Yeah, like you said the proof of stake, and you show us 3 graphs, and you said, so for those graphs, from what I'm understanding, it's like if you get long stakes, the highest weight you will get a highest highest weight you can get. Is that means like rich people, like if is that graph like rich people can get even rich, like poor people can get even poor? Yeah, I'm just a little bit confused.
Yeah, I will say that okay. It's not quite like that, but if you work hard early, you know that even though you are poor, but you are the first people who work, and then even though you earn not too much, but over the time, is the money you earn over the time the time period is the proof of stake. So if you work hard early, if you work not rich, but you work early, over the time you become richer, right? On the other hand, you are rich, then you just go there and then you become rich, right?
Okay.
Even though you don't have time, you don't have the invested for long, but because you're rich, you're still rich. So
okay.
Yeah, so basically okay. Yeah.
But from what I'm understanding, is like basically the more early you will get to work, and so you will also have a lot of money to put in there, and it will be basically get rich people get richer. Then later people come in, they will not get much benefit for their profit. Then I think probably their incentive is getting lower for the later. Yeah.
No, I think you know that okay. I will say that okay. There's a Chinese saying that the stupid bird will fly early, right? 笨鸟相飞. Okay, just
Yeah, yeah.
yeah. I think the other if you change to here, if you are poor people or poor guy, okay, then you'd better work early, right? So every day you work early, and then you will you will become richer, right? But for rich people, okay, they can enter this one later, right? So basically this case, yeah. So you still have the chance.
Okay.
You still have the chance. It's not like proof of work. I agree with you. The proof of work is not depending on how rich you are. You just work there. But the problem with the proof of work is that, okay, we all see that, we all see what is the problem for proof of work. The proof of work is that, okay, let me go to the problem. Sorry. It's used more electricity than 139 countries, right? So the problem for proof of work is that everybody have to work to compete, even though it's equal, and but it costs too much energy, right? In order to overcome such kind of problem, they propose a proof of stake. And indeed, okay, proof of stake will have the problem that richer got richer, but poor got poor. But they still give the method that as long as you work early, work harder, longer, then it's a product of how much you pay times the how long you be there. It will be how rich you are. So you stay there longer, then you will kind of, become slightly richer, right? You still have the incentive. But indeed, okay, compare with the proof of work, yeah, it's a somewhat richer guy richer, poor the poor, but it saves the energy.
Yeah. Okay, thank you. Thank you for I got what you mean.
Sure. But recently, okay, the blockchain want to change from POW to POS, at least for Ethereum. Yeah.
Thanks.
Sure.
Hi, Professor Han.
Sure.
So may I ask you a very high-level question?
Yes.
So I saw like you have a paper with the combination of blockchain and federated learning. So like I'm working in federated learning. Also I have like some collaboration like co-author paper with Tran. So I'm wondering like so like in federated learning, and there's also a very important thing that to incentive mechanism for this users, and I'm wondering if you can have some comments on how to combine these two together and how this incentive mechanism may be used for this combination of these two things.
Okay. And that's a good question. Okay, let me go to that slide. Okay, and first, okay, for blockchain paper, okay, there are several types. The first type is a pure computer science type. This is basically, okay, try to use the crypto to against malicious user. And then the second type is using the blockchain for the different kind of application, like the sushi example I mentioned to you. Okay, you can see most of the blockchain paper belong to this type, but that is a lot of water during the last few years. Okay, and then crypto economy, basically what we talk here is using the mechanism design to link the blockchain. And now it's come to this kind of blockchain with federal learning. For federal learning, okay, then you should think about what is the problem for this federal learning. For federal learning, for example, if you talk about the contract theory, then what is the information asymmetric that happens in this kind of federal learning? And if it's for auction theory, then the auction theory basically conquer this truthful revealment. How could you, truthful reveal? As a matter of fact, auction theory can be considered as a part of contract theory. And for coalition game, basically you can consider, okay, federal learning, okay, you may learn a completely different story. Why should I work for you, right? And you learn very similar to Tran, then probably you will form the coalition with Tran so that you guys have a mutual benefit. So basically, okay, here you need to think about two things. The first thing is that, okay, by using the mechanism design for further learning, what is the problem there that this mechanism design can overcome? This is the first thing. And the second thing is that, okay, why blockchain? Yeah, the blockchain is basically a ledger for everybody so that nobody can lie, right? And then you have to give the incentive for the blockchain for that. So I hope I answer your question, right? So ask yourself why blockchain. But this one you probably already have the answer. The second thing is that, okay, for that kind of system, why you need mechanical design? What thing you're missing, and then you put it inside, and then problem solve. And in this in this talk, we talk about information asymmetric case, and then we use the contract theory, then we overcome the problem. Yeah.
Okay. Thank you very much. Very insightful.
Yeah, sure. My pleasure.
Hi, Dr. Zhu.
Sure.
I would like to ask, are there any implementation, or do you have any intuition about how to implement this approach? Because it can be quite challenging in the context of Byzantine fault tolerance and also in the presence of Sybil attacks.
Yeah, I think you see that, okay, here, basically, okay, in this part, basically we use this pseudo code, but I don't think I can explain the pseudo code. This part is already how you implement it, right? This is basically, okay, this is how this kind of Ethereum, okay, try to have this kind of shard system. So this is already their pseudo code. And then here, okay, later, okay, for this incentive, okay, here we just use the calculation to calculate. So for all this calculation, you can calculate offline or this in another computer, so that in this case, okay, you can hold on a second. You can calculate offline for this one, and then when you really implement it, for example, for this 32 point one, and then, okay, the only thing you need to change for the protocol is for your incentive one, okay, you show them that, okay, this two curve, this is deposit I will get to you, this is the expected kind of reward you will get, and depending, you will select by your own which one you want to select. So in this case, okay, this is a kind of validator itself to select this one instead of the previous one, either only 32. So I will say that, okay, in this case, it's relatively can be implemented, if I understand correctly, can be implemented straightforward. But I totally agree with your kind of the insight in the sense that, okay, and also for Daniel, okay, my current student, when I talk with my Dr. Jim, my former student, I asked her that, okay, in order to implement this one, you have to have the interface to the existing protocol, such that, okay, the people will know how to implement it directly. Otherwise, you know, you're playing the mathematical kind of tools, those economy people already know, right? So basically, okay, the contribution of my student is to design this one and then can provide the interface to the real protocol so that, okay, the blockchain designer can use it. So I like your comment. And as a matter of fact, okay, when my student try to interview, and then, okay, at the beginning, they have the programmer kind of position. And after interview, and they say, hold on, okay, give us a few weeks. We will create a data scientist position for you. Yeah, because my student know how to design instead of just programming. Okay. Thanks.
Thank you.
Yeah, for a paper, okay, for a paper, you can see this pseudo code, which can be implemented there. And also, I will assure you that, okay, my current student, Daniel, will also do the same thing.
Thank you.
Dr. Han.
Sure.
Yeah, but you know, we also add some little bit of applications to the papers we are doing, where we have like we are trying to implement them on a web we have like a web application that users can interact with. And then we also have those kind of codes that, it makes it look practical. It doesn't look like a lot of mathematics information, just like a lot of mathematics. So you can go ahead and then do those kind of like decentralized applications. So you can look into that. And then some of these things are just like, minor codes that you can apply in a decentralized programming scheme. So when you get this result of your mathematics, you just have to put that result in your Solidity programming language. Then you can get that implemented on the blockchain for you.
Sure. Thank you for the support.
All right, any more questions?
Yeah, they have ask a question, and how the recording can be obtained.
Yeah, I'm writing an answer to that one. We'll first share it in our CS SharePoint for local access for internal attendees, and then later will be published in our faculty YouTube channel.
Okay, yeah, please send me the link, because
Yeah, when we have it, yeah, we'll send you the link. We will anyway send you the link before we publish.
Great. I think I'm happy for today's my present. At least my mind is clear. Okay, so I'm happy for what I present. So I will link to my website. Thank you very much for giving me
Yes,
such kind of
so then thank you very much for coming and giving us a talk, and it was very interesting. And then we had good discussions afterwards as well. So if you happens to visit here in Sydney at some point, so you're very welcome to come and visit us and give a talk in person.
Yeah, definitely. I have been to Sydney twice, and I love it very much. Yeah.
So then hope to see you again here.